Hello, my dear students. In this lecture video, I'll be discussing about resistivity and resistance. Okay, but before that, I forgot to discuss one important quantity in my first video, no, about current. So let me just talk about it. If we have current as charge per time, so current as I as charge per time. Okay. Then we have another quantity we call current density. So remember, every time you encounter this word density, it can either be per volume, that's the usual. We can also have per length or per area. No? Diba? We have talked about these different kinds of densities when we had a discussion on electric field calculation. So current density, our symbol is capital J, and it's a vector quantity, so it has vector symbol on top of it. But current is scalar, ha? Yan. Scalar. So walang direction ang current. Uh, no, it has direction, but it's not a vector quantity. Okay? So let's continue. So current density is just the ratio of the amount of current per cross-section area of your wire. So if we get a segment of a wire, and this wire is connected to a closed circuit, and then we just focus on that. So if there's current amounting to I, and then this is the cross-section area, so we say therefore that the amount of current per area is current density. So we can also have another um, expression for current density, which is in terms of the concentration of the charges, free electrons in your wire. And let's take a look at the drift velocity. So we learned earlier that current in terms of these factors here is equivalent to the charge times electron concentration times the cross-section area of your wire, and then you have the drift velocity. So if we divide this by area to get the current density, then current density, aside from it as equivalent to current per area, we can also determine it by multiplying the charge times electron density and the drift velocity. So whatever is the direction of the drift velocity, that is also the direction of the current density. Okay, so the unit is ampere per square meter. That's the SI unit, international system. So we have amp per square meter. Okay, so why did I start with this? It's because the definition of resistivity that we have for this video is very much affected or uh, affected by current density. Okay, so resistivity, if current talks about the number of charge passing through your wire per time, resistivity is a characteristic of your wire. Okay, so that's a characteristic. Uh, it's not a characteristic of the charge, but the wire itself. So characteristic of a wire. Yan. So physically, resistivity is just the ratio of the electric field in your circuit divide ratio of electric field to magnitude of current density. Resistivity is again another scalar quantity. So if we have our circuit, for example, let's make another, so let's say your battery is somewhere here, and then you have your resistors, for example, in series. Oops. 3 resistors in series, for example. So if we have this is plus and this is minus, right? So the electric field is in this direction, no? In the segment here, it's away from plus towards minus, something like that. And then you have your cross-section area of your wire. And if we have your conventional current away from plus into the minus, it's a clockwise direction here. So we say therefore that the greater the resistivity of your wire, okay, then that wire needs to be connected to a higher electric field to bring about a certain current density. Okay, so if you look at the ano here, on the other hand, if the resistivity of your wire is less, okay, then it needs less electric field strength to produce the same current density. Yan. So we say here, if the current density were constant, so if current density is constant or were constant, then we can establish that resistivity is just directly proportional to the strength of the electric field. And if we keep the electric field constant, then resistivity is inversely proportional to current density. Higher current density, higher resistivity means less current density. Less current density means less current per area. Tama ba? Okay, now, so the unit for resistivity will be electric field is volt per meter. And then you also have current density as ampere. So we have our unit here would be, for electric field, it's volt per meter. And then reciprocal of current density would be square meter per ampere. So that this is out. Then that gives us volt meter per ampere. That's the unit for resistivity. Okay, and then resistivity is very much dependent on the temperature of the wire. So if we have the resistivity as a function of temperature, okay, let me look at my código. 1 plus alpha T. So let's put it here. There. Oops. Ayan. Okay. So resistivity is temperature dependent with this relationship here. So this gives us resistivity as a function of temperature. You have resistivity at a certain reference temperature, wherein the reference temperature is usually 0 degrees Celsius or room temperature 20 degrees Celsius. Okay, depending na yan on what reference that we are using. And then alpha here is a certain constant which we call temperature coefficient of resistivity. So we have temperature, so alpha is temp coefficient of resistivity. So it's a constant which depends on the kind of material that you're using. Yan, okay? So if you look at the function here, different metals will have different change in the resistivity, no? As its temperature changes. So there's this reference temperature T sub 0. So let's take a closer look at the variation. How does resistivity change with temperature on three different significant materials in the world of electricity and electronics? And this group of materials are the following. So we have the family of the conductors or metals, and then another important element, no, not element, materials in your field, ECE, no, in electronics would be the semiconductors. And then another interesting material, we have the superconductors. So take a look at the graph here. I got this from our textbook. Okay, but you can see this in any physics book, no? Yeah. So these are the graphs of resistivity versus temperature of three metals. Let's take a look at the three metals, three different kinds of materials. Let's take a closer look at metals. Okay, so what do you see here? The pink curve here is the actual best fit curve for resistivity versus temperature, right? Okay. So if you notice, there's an exponential increase in the resistivity, okay, uh, as temperature increases. So below the reference temperature here, the increase in the resistivity is still not that high kasi hindi pa naman masyadong steep, no? So at zero temperature, the material has its initial resistivity depending on its nature. Ayan, whatever that value is. This is metals, ha? Metal ito. And then if you increase the temperature, medyo there's no significant increase in the resistivity yet. But the moment this reference temperature is exceeded, no? So if the metal is heated, no? Pag tumaas ang temperature niya, then there's an exponential increase here. If you extrapolate this, the slope here becomes greater and greater. Yan. So, why does the resistivity of a metal increase with increasing temperature? Dito, pag high temp na siya. What could be the reason? Pag sinabi nating increase in resistivity, it means that it's not that friendly to current anymore. So, it will lead to a less current in your circuit. So to answer the question, we have to look at the, um, molecular level here. So let's take a look, or the subatomic siguro. So in a metal, so yan. Say for example, we have a metal here. And of course, it's understood that this metal is connected to a complete circuit. There's established electric field, there's established current. No? It's not just a standalone wire. Pero ito lang na part ang dinroko. Okay? So say for example, you have conventional current, no? Or let's talk about, let's say, in the real world, electrons. So you have the positive ions. These are the nucleus of your metal that are that cannot move. Kasi naman the nuclei cannot move, di ba? And then you have the electrons. So let's just say the electrons here in different directions. Now, let's say there's an established electron flow in this direction. Electron. May kuryente tayo from left to right. This is electron flow. I'm talking about electron flow. Ayan. So, as the metal gets heated, no? Let's just say uh, it's been there in the circuit for a long time. Okay, so the wire heats up, the elements in the circuit heats up so that the temperature increases. So as the temperature increases, remember that temperature is associated with the average kinetic energy, molecular. Remember that in our uh, lesson in thermodynamics. So in other words, the greater the temperature, that also indicates greater kinetic energy, and greater kinetic energy is directly proportional, diba, to the speed of a particle. So in this case, as the temperature increases, the positive ions here also get additional energy. So they somehow uh, move or oscillate more vigorously. So say for example, this ion here, it has received additional energy kasi nag-heat up siya. So if initially it just oscillates this much, with additional energy, it can oscillate at this amplitude. Kasi nga may thermal expansion pa, di ba? So if the positive ions here move more vigorously, then do you think the electrons will not have a harder time passing through as one? Diba? Imagine nyo, all of these positive ions moving vigorously. So the electrons now cannot establish much drift velocity. So in other words, the current, no, will have to go down simply because the resistivity of the material has gone up. Ayan. So that's the reason why the additional energy causes the ions here, the positive ions here, to move more vigorously, and then consequently the electrons will have a harder time passing through them, okay, making a complete travel in the circuit. Ayan. Kaya si metal, as time goes by, no, pag medyo matagal na siya sa circuit, everything heats up, then it becomes less efficient as a conductor as its temperature increases. That's why you need to cool things down, 'di ba? It's not advisable for metals uh, to be exposed to high temperature kasi nga mababa yung efficiency niya as a conductor. Okay, now let's go to this one, the semiconductors. Okay, an example of a semiconductor, saan naman yun, is silicon. No? So you will learn more about this when you go to your higher physics, when you study about diodes, etc. But this is the basic of semiconductors. If you look at the graph, yan, you see an opposite trend compared to conductors. Semiconductors are materials that are insulators at room temperature, but as its temperature increases, it now becomes a conductor. So that's the opposite trend that you have here. So in other words, at let's say room temperature, for example, your semiconductor can have a very high resistivity. So let's say at room temperature, for example, at room temp, you have a very high resistivity, so it's still a poor conductor. Poor conductor pa siya. Or in other words, it's not yet a conductor. Okay? Now, but if you increase the temperature, gradually increase the temperature, immediately there's a very high exponential decay here, no? Dramatic drop. A little increase in the temperature and then the resistivity decays exponentially. And then nag-stabilize na siya at a certain low resistivity here. Okay? So what's the reason for this? Let's take a look at the silicon lattice. Silicon lattice. Silicon, I'm sure you know this, that it's one of the most common elements used in semiconductors like diodes, transistors. Why? Because it's very cheap and it's very abundant. Okay? So, semiconductors, the common characteristic, chemical characteristic of semiconductors is that they do not have tawag nito, they're very stable, no, at room temperature. So say for example, si silicon. The valence number of silicon is positive 4. So it means that in its outermost shell, I'm just showing the outermost or the farthest energy level here. It has 4 valence electrons there. Okay, another 4 here. So that if it's just beside another silicon atom, then it has this magic stable number of 8 in the outermost shell. So pag may 8 ka dyan sa outermost shell mo, you are already stable. No? Meaning, it's okay na you do not give an electron. It's okay na you, what's more okay is you share a covalent bond with the other silicon atom. So in this case, since stable siya at room temperature, this is at room temperature, then this is still an insulator. So as an insulator, it has a high resistivity. However, if we heat this up, no? So let's just say you have a heater here or a burner. So by heating it, you are adding more energy into the silicon lattice. It means that you are also increasing its temperature. Tama ba? So once the energy is enough for these electrons, valence electrons, to escape the mother atom, okay, so say for example this one, si electron na ito, let's just say it has enough energy to escape the atom here. So initially or consequently, it now becomes a free electron. So it's as if tapos, pag alis niya, free electron siya, meron ding aalis pa dyan, magiging free electron. The more energy that you add to the silicon lattice, the more free electrons uh, uh, are freed. No? So, the space that is left by the escapee, escapee electron, will now become positive because this will now be what we call a hole or vacancy. So, if a negative 1.6 times 10 to negative 19 coulomb has left, then this vacancy now will have a charge. No? So, ang charge ng hole ngayon, ng vacancy, will be positive 1.6. It's as if equal siya ng charge ng proton. Pero ang difference ng hole from proton is that a hole has no mass because it's just a vacancy in your silicon lattice, whereas proton is really a particle. No? But what's common between them is they both have equal charges. So, ang nangyari dito in the semiconductor, the more energy, the higher the temperature, the more free electrons, then it means that essentially, yung dati insulator has now become a conductor. Why? Kasi meron na ngang free electrons. So if there are electrons, let's just say the electrons here are going, if the drift velocity of the electrons are to the left, meron kang mga electrons dyan, then the holes will also have an apparent motion din, no? So the holes will go to the other direction. So si semiconductors, meron siyang dalawang charge carriers. Meron siyang negative na charge carriers, the electrons, and the positive na mga holes. Pero sa metals, the charge carrier in metals in actuality are just electrons because the protons are being held in its place. Pero pag tawag nito, semiconductor, uh, merong electrons negative, meron ding positive. Okay? Now, aside from being a hole there, what they do to increase the conducting ability of semiconductor is to put impurities. And the process of putting impurities into the hole is called doping. Yan. So, in societal meaning of doping, di ba? It's like abusing, tawag nito, prohibited drugs, di ba? Dope. So, sa electronics, parang ganun din. Impurities, instead of abused drugs, these are actually other elements, no? So, say for example, boron or phosphorus. Ayan. So, the vacancy here, this one, this will be placed with another element. So, let's say for example, boron. Ano ba ang valence? Wait, let me check the valence electron of boron. Do you know? Valence, valence electrons of boron. 5. Ay, no. Ano ito? Wait. Boron. Wait. Stop. Okay, 3. Ayan, let's go back here. Okay, let me erase this for a while. Sorry for a very, very messy No, 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 no. Don't clear the canvas. I just want this. Okay. Ayan. So, let's erase this muna. Okay. So, boron has valence number positive 3. So, if we put boron into the silicon lattice with the process we call doping, so meron siyang, so kung meron siyang 3, tapos merong, so if you have there your 4 for the silicon, and then meron siyang 3 dito. Ayan. So we still have now 1, 2, okay. Am I making sense?